Analysis of variance is a statistical test used to determine if there are significant differences among groups in where their centers are. In other words, we're comparing the means of multiple groups. When we looked at t-tests, those are always comparisons between two groups, either a paired t-test where there's a before and after, or independent samples t-tests where there are two separate groups where we're observing things on. If you extend an independent samples t-test to more than two groups, it turns out you need to use ANOVA because the number of pairwise comparisons goes up as the square of the number of groups, and it becomes unmanageable really quickly. So what we're going to measure is how much of the variation in our data appears between each group mean and how much of the variation appears within each group. So what does that mean? So if you took a whole data set, and imagine we're looking at basketball teams and we're looking at the average height of each team. And you look at the whole data set, there's a whole bunch of variation here. But what we might want to know is if some of that variation that we see here is due to variation not so much just among individuals, but among different groups. So let's say we have three imaginary conferences, the CAA, the Large 12, and the CES, and you can see that each of these conferences has some variation within itself, but then there's also seems to be some of the variation that we saw overall might be explained by the fact that this one looks a little bigger and this one looks a little smaller. So how do we measure that? Well, first we need a null hypothesis, and the null hypothesis is that the group means are equal, which is to say these three groups, we've drawn them, but they're not actually different. They're all just random examples of people from this one population. So the research hypothesis is that each of these, at least one of these three groups comes from a different population, so that its mean is different from at least one of the others. And it only needs to be one. Blue and orange could be the same, blue and gray could be the same. As long as one of these is different from one of the others, you can get a significant analysis of variance, a significant ANOVA. So data like this might be presented like this, where you have the heights in each group, or you have presented like this, where you have each group labeled and each height labeled. So they're the same data. This is a compact way to do it, but it's bad because the computer would think that there's some observation that this 3, this 1, and this 2 go together, and that these are three different variables being measured on the same thing. So we don't do that. We do this, where you have one categorical variable, one discrete variable, which describes group membership, and another continuous variable, which describes what the observation value is for each individual. When you perform your ANOVA, the computer is going to calculate the total amount of variance in the data set. The variance is explained by differences among group means, and the variance that's left over within each group after you've explained the difference among means. And those three variances add together. So the among groups and the within groups together are the total variance. And the degrees of freedom for these variances are the number of groups minus 1, and the sample size minus the number of groups. When you add those two degrees of freedom together, you get the sample size minus 1. And of course, it's the sample size. So we could add up here and say, okay, how far apart? There's mean for gray, a mean for blue, a mean for orange. There's a certain amount of variation based on those three numbers, and there's variation within each of these three groups, and we can compare those amounts of variation. And we get, to make that, we get an F statistic, which is the ratio of variance among groups to the variance within groups. Because the farther apart the groups are relative to how much noise there is within groups, the bigger the F ratio is, the more likely it is that the groups actually have truly different means. So this is a ratio. It's the variance among divided by the variance within. So it's sometimes called the F statistic, sometimes it's called the F ratio. And because each of these two variances have their own degrees of freedom, F statistics have two different degrees of freedom. They have a numerator degrees of freedom and a denominator degrees of freedom. And so what happens is you vary your F statistic. Well, you get something that looks kind of like this, where you have, as your variance spreads out, as your mean spread out, the F statistic gets bigger, and as they come back together, the F statistic gets lower. So it's kind of a measure of how separated the group means are. And when you run an ANOVA, you get these three kinds of data. You have group summaries, and usually what we're mostly interested in is the group identities, the average of each group, and the standard errors. We'll use these for a bar plot in a second. And then you have the ANOVA table, or the F table, which talks about, which is presented like this. These are the two variances we talked about, the variance among, the variance within. The variance is the sum of squares divided by the degrees of freedom. All this stuff is traditional to report. And this F statistic is this 45.7 divided by this 9.3. And the p-value here is the probability of observing an F statistic of 4.9 when you're drawing at random from an F distribution with 2 numerator and 21 denominator degrees of freedom. So we'd only expect to see an F statistic that large, about 17 times out of 1,000. So this is a significant p-value. So we would say that the large 12 is in fact bigger than the other two. So to report it, you have to report the F statistic, both the numerator and denominator degrees of freedom. And then you report the means and standard errors of each group. And if you know it's significant, you report which groups seem to have term values. So you get some kind of thing like this. So F subscript 2, that's the numerator degrees of freedom, comma 137, that's the denominator degrees of freedom. So we're looking at an F distribution with 2 numerator and 137 denominator degrees of freedom. And the F statistically observed is 7.32. And the probability of observing this F statistic is less than 1 in 1,000. So it's different from the other example I showed you. And there we see the large 12. So these are the three means that we calculated. And then the error bars come from those standard errors we calculated. And I think that's the end. Yes. So that's how we do an ANOVA. It's for measuring whether any of these three groups are the same. The disadvantage is it doesn't tell us which one is different. You have to look at the results and decide kind of subjectively which of the different groups are different from each other. And in this case, we're going to say the large 12 is bigger than these other two. And that is where I'm going to stop for ANOVA.